here. And this is going to be, again, distance over time. And it's going to be a max as you get further and further and further out. And this is assuming that the base is moving at the same rate. So there's not like an inner lane and an outer lane and a middle lane that are all moving independently of one another. They're all moving together on a fixed membrane, or in this case we'll use the word disk for now. So we know that the further one out has a larger tangential speed. But what about angular speed? Angular speed. What could you tell me, or what do you think? We haven't talked about angular speed at all this entire year. Similar speed, but now I'm saying angular speed. Angular. So speed is defined as how much, distance covered, right? Distance covered in a time period. What do you think angular speed is defined as? What do you think angular speed is defined as? I'll give you a hint. They all have the same angular speed. All three horses have the same angular speed. Yes and no, but you need more than that. Because they all start here and they stay together is the reason behind it. My question is really, what is angular speed, and what does it have to do with the fact that they're all moving at the same angular speed?
Well, you're saying that none of them, all their angles are the same, so none of them are changing. So I guess how quickly an angle would change.
Yeah, angular speed is how quickly or how much your angle is changing. So they all moved how many degrees to start? What is this? Then they moved another 90, then another 90, then another, right? So eventually they moved how many degrees in a circle? In the same amount of time, right? So they covered the same angular displacement in the same amount of time. So next year, if you take AP Physics, I'm not going to go into much more of this, just to give you a heads up. You'll learn about angular speed, and it's the amount of theta change in a given time period. Okay, so this is angular speed, and this means how much of the angle has changed, or how many degrees, or you'll learn more in math this year about radians, and you'll talk about radians per second. Radian is an angle measure, or degrees per second. Or in cars, revolutions per minute, RPMs. You've heard the phrase RPMs before, it's how fast the wheel is actually spinning or the engine is rotating. Absolutely. Okay? And if you see delta here, it's the same thing for this case, but it would mean, okay? Again, the same idea there, final minus initial. So the amount of angle covered in a given time period is the same for all the horses, but the speed is different. This guy's moving faster. What if you were standing in the center? Hypothetically, I know you can't because it's probably like a column, right? That it goes up from the center. But hypothetically, you're standing at the center of the merry-go-round. What can you tell me about your angular speed? What can you tell me about your tangential speed with regards to what we've discussed already? Give me something.
Would it be zero?
What would be zero?
Like your speed. Because you stay in the center, you're not going away.
So your tangential speed, tangentially to refer, this guy would be zero. Because how much distance do you cover if you're in the very center? And if you're in the center, this is what you're doing. Right? You're literally doing this the whole time as the merry-go-round rotates. I'm not covering any distance. I'm just rotating. So this would become zero right here. So Alex is absolutely right. If you're at the center point of a rotating body, you have no tangential speed. But technically, you have the same angular speed as everything else. Because I just rotated 360 degrees, didn't I? And I would have rotated 360 degrees in the same time that it takes those horses to do one full lap. So my angular speed is the same as anything else, no matter where I am on a rotating body. Doesn't matter if you're at the center, a little further out, further, or the very edge. Either way, all those little dots move together, and they take a certain amount of time, the same amount, to do one revolution. But actual tangential speed is a function of how far out you are from the center. The further out you are, the more tangential speed. At the center, where the radius is 0, this becomes 0, which makes the distance traveled 0, which makes this 0 again. Okay? All right, let's get into a little physics now. So this we already kind of talked about for a minute. This was our intro activity. Okay, objects in circular motion. When you spin something or cause something to rotate that's in circular motion, it has to be connected somehow to you. Okay, so we talked about the force of tension in the rope. We're going to also talk about gravity and electrostatic forces and magnetism and all that stuff, which can also help in these applications. So let's start with the definition of the actual word centripetal, or phrase centripetal acceleration. So centripetal means center seeking. Center seeking. And with this example, again, as I spin this around, it doesn't want to go to the center. As this object is spun, it does not want to go to the center. It wants to fly out from the center. That's the end of this. See, centrifugal effect? It's a common misnomer. Students use those interchangeably. They're not the same. Centrifugal effect is the momentum of the object, its angular momentum really, and its desire to move outward. It's inertial effects, really. But what's keeping it from moving outward is a force of tension in the rope. If there's a force in the rope, there must be acceleration. So let's discuss why this is true. Let's draw another circle. I'll get to the formula in a second. Let's draw ourselves another circle. Let's put a center. Let's put the object right here. Now, let's say that the object is rotating in this fashion. Okay, in a counterclockwise fashion. So at that exact moment in time, if this object were released, it would want to move tangent to the circle. This is like our velocity vector v. Now, why isn't that happening? Is because you have something pulling it back to the middle. Anywhere it is, it pulls it back to the middle. And in this case, it was the rope. Well, the only way something can push or pull is if there's a force. The only way there could be a force is if there's acceleration. F equals ma. With no acceleration, you can't have a force. So there must be acceleration here, but it's not obvious. Because I told you a minute ago that when I was spinning this, I was spinning it with a constant velocity the whole time. Look, I'm not making it go faster. I can make it go faster and try and spin much, much, much faster. Or I can try and spin really slow. And if I spin too slow, there's no tension in the rope anymore, right? But if I spin it with a constant speed, I'm telling you, constant speed, there still is acceleration. How is that possible? Think about your definition of acceleration. It's the change in velocity over time. But I just told you that it's a constant speed. So how could there be acceleration, dude?
Would the acceleration fluctuate?
Would the acceleration fluctuate? The acceleration would not fluctuate.
Because like it's being pushed down and then like it pushes itself back up. Like I feel like it'd be different acceleration, like negative at some point, and then.
Okay, now we're kind of on the right track there.
So it'd be negative.
Kind of on the right track, right?
Would the magnitude of the acceleration not change with the direction?
It has to do with direction. Think back on vectors. Vectors are defined as things with magnitude and direction. So what's happening, good response. What's happening here is this. As the object moves, let's put it here now, its velocity vector changes direction. And because our definition of acceleration is change in velocity with respect to time, even though the actual value, the value of the tangential velocity or speed is not changing, its magnitude, the direction is changing. So if I actually turn from going this way to suddenly going this way and causing a change in velocity, God bless you, and a change in velocity always results in acceleration. Since this is called center seeking or centripetal acceleration, we're going to draw our acceleration toward the center. And this was what Rain was just mentioning. He said, you know what? The acceleration in magnitude isn't altering, isn't changing, yet the direction of the acceleration changes. And this is kind of what Peter was just saying too, because he said, well, the acceleration can be positive sometimes, negative other times, and he meant really like up or down. Okay, we're going to talk about positives and negatives in a minute with radial things. But the concept here is that no matter where the object is, The rope pulls it back to the center. The rope is the easy example, right? It's obvious, it's physically there. So you can see this. That's why I use this as an example. The rope's tension pulls it back to the center. If there's a force pulling to the center, there must be acceleration toward the center.
So is the acceleration and velocity always going that way?
So is the...
Acceleration and velocity always going the same way?
They're always perpendicular to each other. So at a given point, for example here, if the velocity is drawn down, which it would be, the acceleration is inward. The velocity here is drawn this way, the acceleration is drawn this way. They're always going to meet at negative radius. Okay? So both velocity and acceleration are constantly changing direction. Now, the acceleration actually, believe it or not, it's changing angles, but in a minute we're going to talk about forces being positive in, anything into the circle is positive, anything out of the circle is negative. So although it looks like this is changing, it's still into the circle, into the circle, into the circle, into the circle. So acceleration for this case is always going to be actually positive. Okay, we'll talk about that with forces in a moment when we get to that part. Our formula for this, our formula circled in yellow up here, is Vt squared over r. R being the radius, Vt being the tangential velocity. Okay, I can put absolute value around it to make speed, but because it's squared, it really doesn't matter here. Okay, again, I'm not concerned with the negative symbol here because it's squared. And I recognize here that I'm not going to ever have to worry about it. This answer will always be positive. Anything squared is positive. The radius is always positive. Therefore, this answer in the real number set, we should say, really. But this answer will be always positive. What are my units for acceleration? What are my units from previously in the year? Good. Meters per second squared. And they're the same still. If you don't believe me, you can try it. Okay? You'll get meters per second times meters per second divided by seconds. That'll give you meters per second squared. So this is the effect that the astronauts feel. If you spin them fast enough, look how they're related. Spin it faster, you get more acceleration because acceleration and velocity are directly related. If you make the radius larger, the acceleration goes down actually. It goes down because acceleration and radius are indirectly related to each other. So if I had this object here, I'm going to spin it with the same speed the whole time, okay? I'm not changing speed, but I'm changing the radius. And as it gets to a smaller and smaller radius, it's actually undergoing a smaller r value, which makes this number lower, which increases the acceleration. If I had started with it all the way in, okay, and then spun it outward, as I move this outward, if it were actually the same speed the whole time, I'm varying acceleration. That's less, and then this centripetal acceleration, I'm sorry, more, and this as it goes out, it's less, as it comes in, it's more. As it goes out again, it's less acceleration, because I'm increasing the r value. So we want to recognize how they're related to each other. This is different than the previous example with the merry-go-round, okay, going around the circle there. Let's quickly run through an example. This is way too easy of math. We're not going to use something this simple in this chapter, but I want you to start with it at least. So we've got a car that moves around a circular track. It moves with a constant speed. We're told that the radius of the track is 20 meters. And the centripetal acceleration felt is a little bit less than gravity. And find the speed of the car. So in a problem such as this, I just want you to get used to using the new formula for it. So as soon as I see that it's moving in a circular track, and I'm talking about centripetal acceleration, I know already that I'm using this formula. Now, I'll recognize that I'm given a couple things. I'm given the acceleration is 6. And I'm given the track radius of 20 meters. So I've got my givens, I've got my formula. It's honestly just to plug each other for it. Plug it on in. Okay, you could solve for Vt first, and let's practice that so we're all aware. Let's multiply by r, and then take the square root. Okay, and technically this is a plus or minus. Okay, but again, we are looking for the speed of the car. Speed is referring to absolute value of velocity. So really, what we're trying to find out is the absolute value of this stuff. Okay, the absolute value. So the square root of 6 times 20 is the square root of 120. The square root of 120 is around 11. Okay, 10.95 meters per second. So that's the actual tangential speed that the car or the object is going at as it moves around that track. So anything more than that speed will increase the acceleration and possibly cause it to be greater than 9.81, and the driver will start to feel more forces than just gravity alone on the body. Okay? I want to talk about forces for a second, and we're close to the end of time here. I want to talk about forces for a second. So there's a phrase called centripetal force, just like centripetal acceleration. And this is the exact thing that we were just doing. The rope had tension in the rope. That's what this is right here. Centripetal force. It's the force acting toward the center. It's the same exact diagram we just drew, except we're going to draw a force acting toward the center depending upon where the object is. That's my force vector pointing toward the center. The acceleration still points toward the center, but the velocity is going to still be tangent on the outside there. Now, take a look at what's happening here. We know Newton's second law. Newton's second law tells us F equals ma. That's right here. Well, what we consider here is that acceleration, when moving in a circle, is no longer just acceleration. Acceleration, when moving in a circle, is always vt squared over r. Whenever it's acceleration moving in a circle, we use vt squared over r. So we can take this expression right here and plug it in right there. The acceleration itself is vt squared over r. So replace AC with that, and this is what you end up getting. And if you're not really sure what I'm saying, right here, look, there's the acceleration. Right? That's the component of acceleration in yellow. But again, it's ma. Mass times, in this case, centripetal acceleration. This C stands for centripetal force. Some professors, some college professors and AP teachers will call it radial. And next year you're going to learn about radial, the same phrase. I'll use that phrase so we're aware of it. Radial forces mean forces acting in or out. In or out. So for example, if I look at the cup that we just used in the very beginning, when the cup was at the bottom here, what we had was, we had the weight of the cup pulling down. We had the tension in the rope pulling back up. That's what was happening physically. Weight always pulls down, right? The weight of any object always pulls down. The tension in the rope was pulling toward the center no matter where we were. Right? No matter where I am in this diagram, over here, no matter where I am, the tension in the rope always pulls toward the center. So what's interesting to recognize is that this is at the bottom. What if we put it at the top? Well, at the top, we still have weight always pulling down. But now we also have tension. So what we're going to talk about in this chapter, in this section, really in the next class and the next 2 periods, really actually with a lab too, is the concept that sometimes these forces act together and they work together with each other. Yeah, the water, it wants to fall down. The tension in the rope is pulling the cup down. But the effect of it wants to move outward. So sometimes these are going to be added together, sometimes they're going to be subtracted. So let's write a general rule down to conclude. Here's the general rule. Forces acting inward we'll call positive. And any forces acting outward we're going to call negative. So in this case, the cup example, at the top, both of these forces are considered positives because they're both acting inward. But when the cup was at the bottom, the tension was acting upward, or not upward, I should say. The tension was acting inward, and the weight was acting outward from the circle. This is literally pulling it out. The tension was pulling it back into the circle. But here, they're both pulling toward the circle. So at the top, my equation would become the following. That's what it would be. This is, again, F equals ma, the sum of the forces. I've got two forces, and they're both acting inward, so they're both positive. I sum them together. But at the bottom, tension is acting inward, so that becomes positive, but the weight is acting outward. So this equation of motion would be this. So they are different. And if you were to figure out the velocity at different locations, you'll get different answers. And we're going to leave it with that for today, but please recognize this is just F equals mn. Sum of the forces equals m times n. Okay? If you have any questions or want to start looking at this after school, feel free to look at the homework, you can. If you have questions on your project, please ask me. Please email me your groups and what you're working on. If you haven't done so already, I have 4 groups, that's it. And there's about 10 groups. I need the rest of the emails to me, please. No. This homework is not due tomorrow for you guys. We have to finish up the section. But you can absolutely start if you like to. You do. Alexa, come back. Thank you, Maria. Sorry, Alexa. Just take this before you go.
Thank you.
Obviously, these days it's been more of a function of who comes by. So if a lot of students come by, I'm usually here for a while. I'm here for like a half an hour or an hour. And sometimes if nobody's here, I'll leave. What's your plan? Okay. You're doing running club, right?
Yeah.
Okay. I might be here, I might not. Feel free to check up. I'm really not sure. It depends on if people stay around today. Because I know that in the next 2 days, I will definitely be here. I'm trying to think. Today it's Monday. You can come by, check, if you want to get one to work, you have questions.
Of course.
Just get work done? We said both or we said both? If you have anything you want to like really quickly ask before you go to track, but it's usually wait for you guys, right? You want to be late?
Yeah.
So go for now, and if we're here, you slip it back and I'll talk to you.
Anytime.
I probably will still be here for. I've not worked with you, but I'm tired. I'm going away all weekend. I didn't sleep much, to be honest. So I'm trying to just catch my sleep. I'm really tired. So I might go home today, or I go home to buy. I'm tired. But if not, I'll be here tomorrow after school on Wednesday and Wednesday morning. Okay? Sorry, Alex. Hey, thanks for asking. I appreciate it. So, Rain, how you doing?
Good, how are you?
Good to meet you.
Nice to meet you.
Where'd you come from? Where are you coming from school-wise? Mathematically, physics-wise, science?
Well, basically, I came from Concord,
Okay.
College High School,
Okay.
and we just finished.
Any questions at all? Okay.
Momentum and Physics.
Oh, perfect timing. So did he show you the Moodle page yet?
Yes.
Okay, so on the Moodle page is all the notes for the entire year, every video from every class.
Right.
If you've covered it already, you don't have to make anything up.
Right.
So, but it is on the final.
Right.
So everything in the first semester is covered on the final.
So
you have to know it's there.
Okay. Yeah, I think I looked at most of it, and there's only like one slide where I wasn't sure if we covered or not, but everything else I think we did.
Oh, then you should be pretty set. Topics-wise, if you want to see the topics, they're listed on the syllabus.
Right.
So you can quickly remember from today. Let's quickly look at the idea of centripetal force, and these are pretty easy ones. And then we'll get to the math problem itself. So when an object swung on a rope, what did we say was the force that was providing it again? When it's on a rope, it's tension, very good. So that's the first one, and we already did this, so we can kind of just fill that one in for now. It's tension for sure. How about a car? When a car is going like on an exit ramp, or an entrance ramp, or around like a racetrack, like NASCAR style, what keeps the car from slipping, from sliding outward? What force? What force? Remember, it's always forces that we're looking for. What force provides some sort of grip? What's the force that provides grip? Friction. Very good. Okay, and you might use the word traction for cars. Traction is the physical grip between the rubber tire and the floor, which is friction still. But traction is not called a force. How about a roller coaster when it's in one of those loop-the-loops? A roller coaster. And yes, it is loop-the-loop, which is weird, right? Did you ever know that? Did you think it was loop-de-loop?
Yeah.
Everybody thinks it's loop-de-loop. So did I. Then I read this in a book, and I was like, no way. It's not loop-de-loop. But you say it as loop-de-loop, and you're good. Anyway, a roller coaster, when it's going through there, what prevents the roller coaster from literally launching off into space or launching off into whatever, into the atmosphere? What does it? Partially. Gravity helps when it's, but on the bottom, gravity's pulling outward. On the top, gravity's pulling inward. So gravity changes, but something else doesn't.
Is it friction again?
It's not friction this time, no. Normal force. a roller coaster going around a loop-de-loop is the same as the cup swinging around. The cup pushed back with normal force so the water couldn't fly out. The tracks of a roller coaster push back so that the roller coaster can't just go off into space. So this is definitely normal force. And at times it's gravity also. That's the thing. When it's at the top, gravity is pulling back to the middle. So gravity helps when it's at the top. But at the bottom, gravity doesn't. How about this one? This is a little tricky. Okay, so we're looking at an airplane in the same form. Have you ever seen like Blue Angels, I think they're called? They do all the stunts on Jones Beach out on Long Island. July 4th or something they do that. What keeps an airplane from losing its control when it does a loop-the-loop itself? So imagine it spins around, comes back around, and continues. What forces are acting on an airplane? We have never talked about these forces in this class yet. We will talk about it with fluid mechanics later in the year. Yep, so he's right. What is the name? Anybody know the name of that force that causes airs or the plane to get pushed up? He's right. It's the air flowing underneath and above the wing. Lift force helps it to move up. And what's the force that prevents its motion? Not that, no. I like that though. Lift and drag. Good. Lift and drag force, both. So this is lift and drag, depending upon what part of the loop it's in. Okay, lift and drag. Lift force is helping to lift off. That's why you call it lift off. And then drag force is like friction, pretty much. How about an electron in orbit? An electron in orbit. This is one that the phrase is not necessarily something you might know, but the idea you should know. Okay, the idea you should know. If you think about an electron around the nucleus is a positive charge, the electron is a negative charge. So theoretically, what is the force that keeps together two opposite charges? We haven't done it yet in this class, that's why. I just thought maybe in chem you might remember this. It's not magnetism, but it's like that. Right? Magnetism is a north and a south pole with the actual changing of the magnetic domains in the particle. This is not, but it's the same idea. Like north and south attract, right? Positive charges and negative charges also attract. What's the force between a positive and a negative charge called, though? Do you remember this one or not? I don't know if that's the right phrase for it. The actual force itself. Magnetism has to do with poles. It's one of the electromagnetic. It's electrostatic force, but yes, which is like a subset of the EM category. Okay, but it's the electrostatic force. Electrostatic force. And finally, a satellite in orbit. Satellite in orbit. What keeps that? Like the moon. The moon is a satellite, right? What keeps the moon from going off into space? Gravity. Okay, the gravitational force. Okay, and this is gravity between two objects. And we'll talk more about that actually in this section, but not until tomorrow or the next day. So I want to press forward onto the next thing. So let's take a look at this example here. The example says the following. Imagine you're doing what's called a project adventure course. And in like a lot of these courses, you have examples. This was like a middle school thing I remember doing. You had like the gym floor was lava, and then there was like a mat here, a rope. There were like little what looked like skateboards all over the place. You would have to find ways to get from island to island without like touching the lava. It was like I don't know. We did this in middle school, I remember. So I was thinking about this problem the other day because I wanted to do an example with a rope. But why else would you swing on a rope? Maybe if you were at like a lake house. Have you ever seen people like swing on like a vine, just like go into the water? But like something like that, grown-ups I think they do it in, right? Yeah. So besides that, like you're not going to really be swinging on a rope anytime soon. So I was trying to find something applicable, which I'm trying here. It's a stretch. So imagine you're on an island over here. You need to swing from this island to the other island. The rope length is 8 meters. It can withstand a force of 750 newtons. Your mass is 60 kilograms. And the question is, what's the maximum speed you can swing? The maximum speed. And what am I alluding to? If you swing with a speed higher than that, what do you think is going to happen? I like that though. But no, you don't go around. That's like the cartoon where the kids go over the handlebars and they go to another world. You don't go around. There's a ceiling above you. But you could theoretically, if you swing too fast, hit the ceiling. What else though? Look at the problem and think about what I'm referring to.
Breaks the rope.
Yeah, it breaks the rope. And the reason you can elude that is because it says it can withstand a force. That's the maximum tension that the rope can actually have. 750 newtons is the maximum
Go
tension.
back to last year's tug of war.
That's right. Great example, actually. You know, not to like distract us and go on a tangent, but I'm gonna. In the tug of war last year, do you remember when they were talking and it snapped? After that, I'm not joking. A lot of the juniors were like, Mr. Howell, what happened? Explain. And I'm like, listen, we're doing tension right now, and it was actually this topic that we were doing, and it happened around the same time period. Yeah, so we were talking about the maximum allowable tension and how it's just
We were
cheaper.
all looking at you, and then like Mr. Johnson or something, and we were like, this is gonna snap.
Oh, it's definitely gonna
You
snap.
brought out the thinnest little.
Oh yeah. It was. Do you remember the rope when it came out? I'm like, this is not gonna work.
It was like nylon.
Yeah, it was a rope with like 3 braids in it or something. Yeah, it was not meant to withstand that force. Yeah, this year we were on the side, the teachers, and we were all looking like, it's gonna happen again. Is it gonna happen again? It's kind of exciting to see it happen. I'm not gonna lie.
We should have gone like cheapy rope again.
Just to mess around. It's true. Get all the seniors against the freshmen.
Exactly.
I wouldn't know. Seniors wouldn't remember. All right. So in this problem, we have to consider the fact that we have to find the maximum v, or tangential velocity, is the goal. So let's ask this question first. If I think about a rope, let's draw ourselves a little pendulum, right? A rope is a pendulum. Here's the person right there. Here's one island. Here's the other island. They need to swing along this arc or curved path until the rope ends up over here with the person over there. And then they dismount and land on the island. So the question I'm going to pose is this. When are we interested in the person's motion? At what point in time? In the beginning? In the middle? At the end? Somewhere else besides those 3 locations? When will the person provide the most force or tension in the rope? At what point? Again, in the beginning before he or she starts, at some point on the way to halfway, at the halfway point, at some point along the way to the end, or at the end. When is there going to be the most pull on the rope? Why in the middle? You're using logic right now, but there's a mathematical answer for it.
Because something to do with potential energy.
Yeah, absolutely. Something to do with that.
Something to do with mass.
I
don't know.
You had it. You're on the right track.
Isn't it because the mass and also the gravity, like mg and like
Which way does it pull?
the down?
Okay. At the bottom, the mass and the weight physically is pulling down, which means all the weight pulling down is actually acting against the rope, right? So it's a higher chance of snapping. Then in the beginning, when gravity pulls down here, it's a vector component that's acting against the rope. That's one way to look at it mathematically, absolutely right. But how about back to potential energy? What else? At the top, all the energy is potential. But at the bottom middle, what is all the energy? Kinetic. And kinetic energy is the energy of motion, isn't it? So when was the object at the highest speed was always the bottom we talked about. When the pendulum was released, the speed was 0. At the bottom, it hit max speed, slows down, slows down, slows down, stops. Speeds up, speeds up, speeds up, slows down, slows down, slows down, stops. So it reaches max velocity at the bottom, actually. So it's at the bottom that we're going to have the max velocity and the most tension in the rope, or the most pull on the rope. So that's where it might snap. So what we do for this problem is we physically analyze it at the bottom. Okay, at the bottom is when we look at a free body diagram. And we did this. We did it yesterday with the cup. That's why I made a point to point about the cup. When the cup was at the top, we had one free body diagram. When the cup was at the bottom, we had another. So let's draw our free body diagram in blue. When it's at the bottom, we've got the weight pulling down. We've got tension pulling back up. And if I think about circular motion, radially inward is a positive force. So that means that's Ft. Radially outward is a negative force. So that's going to be a minus mg. And whenever an object is in circular motion, we set it equal to ma. But what's a really? From earlier this lesson, what was the definition of a? When it's in circular motion, we had a formula for a for that. So we don't write ma. I mean, I could write ma, but then I have to replace a with another formula. What was the formula? Look back in your notes. What was the formula for a? We just wrote down. Yesterday it happened, yeah. Yeah, there it is. So if I want to write it like this, I can. Some of you are like to write it separately, but I could also just write mvt squared over r. But the key here is this. whenever something, write yourself a note, whenever something is moving in circular motion, the sum of the forces is always going to equal this expression right here. And really that's what we're doing. We're saying the sum of the forces acting in circular motion is equal to m times a in circular motion. And this Fc is really the radial forces, radial. In your text and a lot of text uses the letter C for centripetal. But it really means all the forces acting inward or outward at that moment in time. Okay, in which that moment is the bottom of the path. And at this point, it becomes just a plug and chug problem. Okay, we just have to actually plug in numbers now. So we're trying to figure out the velocity that is the maximum. So what should we set the tension equal to? We want the max velocity. What should we use for tension? The maximum allowable velocity. How much tension will be in the rope when it's at its max possible velocity? How much tension? Just below what number? When it's at the most speed it can be before snapping, what would the tension be around? What number?
749.
Yeah, like 749.99, all right, that whole idea? So really what we're doing here is we can just set the tension equal to 750. If we set it equal to 750, the answer we get will be the most velocity possible because that most velocity causes 750. So let's set the tension equal to the maximum allowable tension, which is 750. That's the maximum allowable tension. So as a result, when we get velocity, it will give us the maximum allowable velocity. After this, we know the rest. That's the only key right here. Putting that to 750 is a little, not a trick, but it's because we're trying to figure out when is this going to snap? At what velocity will the rope snap? That's the tension that's going to cause the rope to snap. So let's call it the tension right there. And then we've got minus mg equals mvt squared over r. What's r? What's r in this problem? Yeah, how come? Which is really the... Very good. So from the pivot point to where you're going, so complete the circle if you need to. It's not a perfect circle, I apologize. Complete the circle. This is really a radius, isn't it? The rope length of 8 meters is really the radius. So really we have L equals R, which is really just 8 in this problem. The length of the rope is the radius, which happens to be 8 meters. All right, and then at this point it's just solve, right? Subtract on the left, multiply by 8, divide by 60, square root it. And for the sake of time, I kind of want to get into the lab. I'm just going to tell you the number. We're going to get 4.6. Now, because I took a square root, technically the answer is plus or minus 4.6. But what is this problem asking us for? Is it asking for velocity? It's asking for, instead of velocity, similar but speed. Very good, which is just the magnitude. So again, the velocity is technically plus or minus 4.6. So I can write that, but then on the next line, here's what I'm going to write. Okay, the magnitude, as Ray said, or the absolute value of the velocity is the speed. It is the speed. So we don't need the plus or minus because we're taking the absolute value of that. So anything more than that number, what will happen? Anything more than 4.6 meters per second, the rope will snap. The rope will snap. So let's use a less than or equal to sign instead. Does that make sense? Okay, then I'm using less than or equal to here. Because again, the rope will snap anything greater than that value. All right. I needed to get that spiel done before the lab. That's the only reason I wanted for that problem, because the lab relates to this topic, and I didn't want you to have no knowledge of this beforehand. We're going to finish, or actually I'm going to ask you guys tonight, listen carefully, tonight, so this is the rest of the notes, it's not much. So there's the gravitational force, the definition, and then this example 4 and 5. Okay? So if you could, I'd really ask you to please watch those tonight. I'm not going to make your homework due tomorrow. I have the other class homework due tomorrow for this section, because they watch the rest of this over the weekend. Their homework's due tomorrow. I'll push your homework due for another day. I think a Moodle might say tomorrow for this. But tonight, watch gravitational force, example 4 and example 5. Okay, please take notes on this. We will discuss it in class, but I don't want to spend 40 minutes discussing it when I can spend like 10 asking questions. Okay? I want to give you more material for this next test. So do that tonight, please. Your labs will not be due tomorrow, okay, so you don't have to worry too much about these yet. But I do want to quickly talk about them. Want to help me with the demo?
Yeah.
It's really simple. You remember last
Yeah,
time.
this is kind of.
Once you get the hang of it, it's not bad.
I know, but I have to do it in a trash.
Trash on it?
Yeah.
Alright. So here's what we're going to do for this lab. The goal of the lab is going to be using simple mechanics and nothing else to determine the mass of this stopper. You can't use a scale, but just from mechanics, just from the forces in centripetal and circular motion, you're going to be able to determine the mass of that stopper.
Yeah, but
Okay? I'll do this.
try to do it straight.
Yeah.
It's not floppy like that.
So your goal, if you look at the front page of the
There
lab,
we go. That's
your
it.
goal is going to be to spin this around, yeah, like that. Now, the key, though, is that right now his hand is touching the rope.
Yeah.
He can't be, and he can't be holding on to this either. So at first, you're going to have to spin it a couple times, and it's going to be a little bit tricky. I'm going to recommend that one of the two of you spins the other times. Don't switch who's spinning, because one person might be consistent and the other person might be totally different. So whoever's better at spinning it should be the spinner the whole time. You're going to work with one other person in this. Okay. Now, once you get it, kind of see how it's at an angle.
Yeah.
He needs it to be more level.
That's
You
why
want
it's fat.
it's hard. You want me to do it? I can do it. I do it every year. That's the only reason I can say it. I literally have gotten to be a pro at this, which is annoying, just because I do it every class. So the way to start it, honestly, is to start it like a little bit lower or higher than the actual marking. You're going to see there's a marking here. That's 20 centimeters. The next marking is 30 centimeters from the mass. The next marking is 40 centimeters. And that's going to be your radius. That's a radius of 40 centimeters, 30, and that's 20 right there. So when you do this, the way to start it is to actually hold the rope first, even though you're not supposed to. Hold the bottom of the rope with your hand, and just get a little motion first. Okay, once you get it down pat, try to let go, okay, and keep this where it is. Your goal is going to be to keep that little black mark right there at the top the whole time, so that the radius is consistent. The radius right now is 20 centimeters the entire time.
The trick to it is if you have it consistent, the rope's not going to move up or down.
Correct. Watch what happens as I spin faster.
It's going to go up.
It's pulling the mass up. Spin faster, it pulls even further up. Now to get it back down, you actually have to tug on it. If you just stop and go slow, the mass is just going to stop. Okay? So the goal is to get it to move at a constant velocity, and once that happens, kind of let go. See my pinky? Watch what I'm doing. With my pinky, I'm kind of holding the rope at first, and once it's moving constantly, I let go. Another technique is this. If it's too far up, like that, you can just tug down on this till it's in the right spot. Get it to the right speed, and then let go. Okay? So that's a good way to keep this in constant motion. The hardest part of this lab is actually getting the data. Okay? It's not easy to do it. Now, what you're going to do is one person is going to time, one person is going to spin. I highly recommend you don't time one cycle. What do you suspect you should time? How many cycles?
3.
Something more than one, right? 3 is easy, 5 is easy, maybe 10.
Yeah.
Because if you time 10 cycles, what can you do? Move the decimal one spot. If it takes 6 seconds for 10 cycles, it takes 0.6 seconds for 1 cycle. So time 10 cycles, just so one person times it, when they're done, just move the decimal one spot. The other part that's important is to recognize when you're timing it, you need to make sure that this crosses the same location every time you count. So watch what I mean. Ready? Set. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Stop. So I actually counted 10 cycles by starting at 1 and stopping on 11. If you want to start as the first cycle as 0, you can start and go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'm counting every time it passes the same location. Does that make sense? Don't just arbitrarily count to 10. Pick a spot where the stopper is, and every time it crosses that spot in your path, count 1.
Oh, don't do something on the person also. Because if you try doing that, for some reason, just like messes with your perception.
What do you mean?
Like for instance, if you were spinning it right now, and I was doing it, I was trying to make it the tie. But then like when you're looking down at the tie, and it's going around, you see it a lot closer than it actually is.
So you're saying don't do it when you're
You
angling
messed
at
up
the
all
person.
my times when I was trying to look at the person, so just put like a finger there. or
That's a
something.
great point. So maybe on the side, use that as a marker. Every time it crosses the finger, okay? Go ahead. Sometimes the mass comes apart, just screw it back in. Because you're spinning it, it's going to spin naturally. There's a lot more to it, but today I'd like to get the data collection done. Clear? So that's what you're doing. 10 cycles, averaging it, putting it in one spot. You need to do this 5 times. So 10 cycles, 5 times for the first marker of 20 centimeters. Then 10 cycles, 5 times for the middle column of 30 centimeters. And then again at the end for 40 centimeters. If what I'm saying isn't actually clear yet, you should probably just also read the procedure at the top. The procedure at the top and the theory on the first page could help you a little bit. I had the other class read that, they had a little more time. You don't have as much time right now to do it. You have about 20 minutes or so. Okay, you can easily do, you can do this in about 15 minutes. It's not going to take you the full 20 minutes. So if you want to sit back for a minute and read the procedure so you're sure of it, do that. But once you get started, it will not take you very long. Use your iPads to time, please. Do not use your phones. Use your iPads to time. What else? I think that's it, yeah. That's the only thing we need to know for today. Right?
No.
Okay.
So what is this due?
Probably not till Friday or maybe even Monday when we're going to have your test. I haven't decided yet. I'm going to see how it goes today and see how we work with it tomorrow. Okay, it's going to be two days. Friday is one of the classes doubles. You guys?
1, 2, 3.
And Friday we'll most likely finish up this lab and do a little bit of a simulation from 9-4 and then review in the second period. Because I want to cover 9-4 before Friday, so that's not, you know? So then your test is on Monday, right?
Awesome.
Okay, so there are 7 apparatuses set up. We have 2, 4, 6, 8, 10, 12. There are 12 of you here. So there's only 6 groups needed. Work with one other person. You definitely have to work with someone else. You can pick, or honestly, whoever's left behind, you want to do that, that's fine too. Or I can pick groups for you. It doesn't matter to me. Come over and get an apparatus from me though, please. Don't pick any of these randomly. Some of these from Neil Honors class. They made their own. I made them for you to make it a little bit easier to be honest. I got it at the time.
It's kind of busy texting.
Please call Gus or I over to help if you're having trouble. If you want to check your data, I highly recommend you check your data after you do your first 5 runs of 20 centimeters. Okay, your first 5 runs of 20 centimeters, then check your data with me. If your mask comes unattached or disattached or whatever, just let me know. I'll come by and fix it. Correct. Rob, you got one yet or no? You got one ready? Order out? Why don't you use the 2 of you and the 2 of you? Is that okay? It doesn't matter. You can all 4 work together. It doesn't matter. You can talk among them, but you have 2 different apparatus, so you both do it.
Let's get this small. If you want.
Oh, another recommendation, sorry, I should say this. You probably want to spread out. Like, the 2 of you right next to each other might cause trouble. Yeah. And when you're spinning it, you need to really put your arm out in front. Okay? It's not easy. Practice for a little while. Those are the forms.
No, I know. Sarah.
Alright, let's read them.
Hey, Pete, Chris. You don't mind, right? Because I've already seen these come in.